guys, in this video today I'm going to talk about your solubility rules, your predicting products, net-ionic equations, and including how to draw a particulate diagram, and then probably one of each of the stoichiometry problems we've gone through, along with limiting reactant. But first thing we're going to talk through is your solubility rules. And I want to go ahead and say, in this video we will also be balancing all of our chemical equations, so you get a little bit of that thrown at you as well. So I've gone ahead and kind of annotated the solubility rules just so we can talk through them better and you get a better idea of what you're looking at. So, first off, it starts by saying, Rule 1, all common salts of group 1 elements in ammonia ion are soluble. Okay, what that means is all your metal-nonmetal compounds or your ionic compounds are soluble if they begin with a group 1 element, so you have a hydrogen, a lithium, a sodium, potassium, rubidium, cesium, or francium, or the ammonia ion, NH4 with a 1+. They're soluble, so that means they're going to get the AQ aqueous symbol. And I did include hydrogen in this because all of our strong acids are going to be soluble as well, which are going to be the acids that we're dealing with right now. Rule number 2 says all common acetates and nitrates are soluble. So what that means is when you have an acetate, which is C2H3O2 with a 1-, or nitrate, which is NO3 with a 1-, they're also going to be soluble with the AQ. So your group 1s, your ammonias, your acetates, and your nitrates are almost always going to be soluble, so they get the AQ symbol. Number 3, this is the most confusing rule just because of the wording, but it says all binary compounds of group 17 elements other than F or fluorine with metals are soluble except for those of silver, mercury 1, and lead. So binary, like a bicycle has 2 wheels, a binary compound has 2 elements, a metal and a non-metal. So that means polyatomics are not involved here because we have all these special rules at the end for polyatomics. So your non-metals part is going to come from group 17, and since fluorine's taken out, we have chlorine, bromine, iodine, and acetylene. And those all are going to have a 1- charge. Your metal, it's any metal except for silver, mercury, and lead. And those are all going to give you the solid. Everything else gets the aqueous symbol, or that means it's soluble. Our next one, it says sulfates are soluble except for those of barium, which is a Ba2+, strontium, which is an Sr2+, lead, which lead can be Pb2+, or Pb4+, calcium, which is a Ca2+, silver, which is Ag1+, and mercury, 1, which is Hg with a 1+. So all sulfates are soluble, so they get the AQ designation, unless it's with one of these elements I just listed, and then it gets the S designation. And sulfates are SO4 with a 2-. Okay, Rule 5. This is kind of what I was referring to in Rule 3. So except for those in Rule 1, so that says except for group 1 elements or ammonia, carbonates, which is a CO3 with a 2-, hydroxides, which is OH with 1-, oxides, oxygen with a 2-, sulfides, sulfur with a 2-, and phosphates, which is PO4 with a 3-, are insoluble. They get the S designation. So the only ones that get the AQ or aqueous designation are going to be if it's a group 1 bonded to one of these, or if it's ammonia bonded to one of these. Those will get the AQ or the aqueous designation. So now that we've gone through our solubility rules, let's go ahead and work through our first problem. This one's going to be a net-ionic equation / predicting products problem because we need to do a little bit of both. So my instructions say predict the products and write the complete balanced molecular equation for each problem, including phase notations. Then write the reactions as ionic equations, cross out the spectator ions, and write the final net-ionic equation. Woo! Let's start with our first step. We're going to go ahead and write out what we have. So silver, which is Ag1+, nitrate, NO3, 1-. So 1 to 1, Ag, NO3, reacts, which again just means plus, magnesium, Mg, 2+, sulfate, SO4, 2-. Notice it's a sulfate, which is the polyatomic. Sulfide refers to sulfur, but this is sulfate. So a 2 to 2, so you get Mg, SO4. Okay? Now let's predict these products. This is going to be a double replacement. I like to do a double replacements, is leave my metals in their same spots and just switch out their partners. So I'm going to have Ag and Mg. So nitrate is now going to go with magnesium, and sulfate is now going to go with silver. sulfate has a 2 minus and silver has a 1 plus, so it becomes Ag2SO4. Magnesium has a 2 plus and nitrate has a 1 minus, so I'm going to put this whole thing in parentheses and put a 2 on the outside. So to balance this, I have to look. I like to do my balancing this way, just so I can see what is happening in each one. I can leave my polyatomics as 1 unit because they exist as polyatomics on both sides. So 1 silver, 1 nitrate, 1 magnesium, 1 sulfate. 2 silver, 1 sulfate, 1 magnesium, 2 nitrate. Okay, it looks like the best way to balance this is just to stick a 2 right here, because that gives me 2 and 2. Okay, so that's how I balance this equation. I'm going to go ahead and erase this, just because I'm going to run out of board space if I don't. Now I have to put my phase notations, and I'll have my complete molecular equation. Okay, so my phase notations. For nitrates, nitrates are rule number 2, so I'm going to focus on silver nitrate and magnesium nitrate. Rule number 2 says all common acetates and nitrates are soluble. So I get to put AQ with the 2 nitrates. Okay, sulfate rule. So that's going to refer to this one and this one. Your sulfate rule, which is rule number 4, says all sulfates are soluble except for those of barium, strontium, lead, calcium, silver, and mercury 1. It looks like I have a silver right here, so that's going to be my solid. And magnesium sulfate wasn't listed as one of the insoluble ones, so I have to write AQ. So this is my molecular equation. So now I have to come up with my ionic equation. So in my ionic equation, I normally write it on 2 lines. I write my reactants across the top, and then I write my products underneath. And the arrow, or the yield sign, is going to designate if I'm on reactants or products. So here's the thing about ionic. Aqueous compounds become ions. Everything else is going to stay as 1 compound. Okay? So if it's aqueous, it's going to become ions. So the first one, I have 2 Ag 1 plus aqueous plus 2 NO3 1 minus aqueous. Notice that the coefficient 2 went to both of these guys. Next, I have Mg 2 plus aqueous. I know it's a 2 plus from up here when I looked. And I can look on my periodic table and see that magnesium exists in group 2. Plus SO4 2 minus aqueous. So those are all my reactants. I'm going to write my products on a second line, just because my smartboard doesn't go on forever. Okay, my solid, leave as is. I can't break that down. It's a solid. But I do have an aqueous compound on here. My aqueous compound, Mg 2 plus aqueous plus 2 NO3 minus aqueous. So to get from my ionic to my net ionic, I have to go through and identify my spectator ions. My spectator ions are ions that appear on both sides of my yield symbol or my arrow unchanged. So that means they have the same coefficient, the same charge, and the same phase notation. If they're the same on both sides, I can cross them out because they're spectator ions. Okay? So my spectator ions in this case are going to be the ones that are not involved in making the solid. So nitrate appears on both sides the same, and magnesium appears on both sides the same. So all I have left is 2 Ag 1 plus aqueous plus SO4 2 minus aqueous, and that yields Ag2 SO4 solid. This is how I check. According to net ionic equation rules, they have to be balanced both by charge and by mass. By mass means I have to have the same number of atoms on both sides. So I have 2 silver here, 2 silver here, 2 sulfate here, 2 sulfate here. By charge, okay? 2 times 1 plus gives me a 2 plus. Then I have a 2 minus, so 2 plus 2 minus equals 0. and neutral compound 0, so it's 0 on both sides. So this is my net ionic equation. My next step is I want to show you how to do a particulate diagram of this equation. So my particulate diagram. I started out with AgNO3 plus MgSO4, so that's going to be my two compounds down here. Okay. So AgNO3, MgSO4. So what your particulate diagram shows you is what your two beakers of ions would look like when you combine them into one beaker to get your product. Okay? So I know that these two are aqueous from my ionic, or my molecular equation. Okay? And the product they formed was a solid Ag2SO4, or silver and sulfate, and an aqueous magnesium nitrate. Now, if you heard me kind of blunder my words a second ago, it's because I was getting ahead of myself. So your particulate diagram is basically showing you your ionic equation. I'm just showing you the ions I have in solution. So in solution, I'm going to have Ag1 plus and NO3 minus. Okay? My two ions just floating around. I don't have to put their aqueous because they're in my solution. Next one. Mg2 plus, SO4, 2 minus. Notice that these are at a 1-to-1 ratio, okay? And that these are at a 1-to-1 ratio, so I can draw them the same. I could draw as many AgNO3s as I wanted in here, as long as I made them in the same 1-to-1 ratio. Okay, last one. When I have a solid, generally I think it's gonna sink. So I'm gonna draw my solid at the bottom, kind of like this rock, weird formation type thing. That's what tells me that it's a solid. So my things that were involved in making it, these guys are going to stay over here. What I have left over is I'm going to have an Mg2 plus and an NO3 2 minus. Oh, I left one thing off. This is why it looks funny. When I balanced it earlier, I started out with 2 of these. So I'm going to go ahead and draw 2 of these to begin with. Because then I have my Ag2 and I actually have 2 NO3. Oh, that's with a 1 minus. I didn't put a 2 minus. There you go. So I'm showing that I start with 2 silver nitrates, 1 magnesium sulfate. I end up with 1 magnesium ion, 2 nitrates, which is totally what that says, and my solid. Okay? So that's how I do my particulate diagram. The next thing I'm going to do is our first stoichiometry problem. So we are going to do a mole-to-mole ratio. And I'm going to set it up in this particular fashion because it's going to make it easier for us to solve more complicated problems in just a minute. Now I know there's like a bajillion different ways to do stoichiometry problems, but I'm going to do it my way, and I'm consistently going to do it the same way so that you can follow my work. So the first thing I always have to do is balance my chemical equation. So I have nitrogen, hydrogen, and oxygen. I start with 1 nitrogen, 3 hydrogen, 2 oxygen. 2 nitrogen, 2 hydrogen, 1 oxygen. Okay? When I have a 3 to 2 type of thing, what I like to do is I just want to find the smallest common factor, which in this case is going to be 6. So I'm going to put a 3 here and a 2 here. So I end up with 2, 6, 3 times 2 is 6, and then I have 3 oxygen, okay? Well, that's not going to work out too well because now my oxygen number is off. So I guess what I want to do here is I'm going to throw in, well, I could double everything, so let me try doubling everything. If I make this a 4, and this is 6, what'll happen here now? Okay, so I have 4, then H, 3 times 4 is 12, okay? That gives me 12 and 6. And looky there, I can put a 2 here, and that's going to give me 4. And I can put a 3 here, and that's going to give me 6. And everything's in its smallest ratio, so that's perfect, because that's going to save me some time as well. Again, I'm going to just erase to save some space. And I'm going to start off by writing down my given. So I'm given 8 moles of ammonia. And I want to find out how many moles of water. So I always put my given over 1. I put it over 1 so I don't accidentally multiply it on the wrong line. That's the whole secret to 1. Okay, mole-to-mole ratio is what I get to use now. Now, the units I have on top here are going to slide down here so that I can cancel them out in just a second. Because I want to be able to cancel out my units. If I have moles of ammonia and I want moles of water, I can use my mole-to-mole ratio to get there. And what my mole-to-mole ratio is, I use my balanced chemical equation that says for every 4 NH3, I have 6 H2O. So then I just do a little math. 8 times 6 is 48. What are my units? Well, my moles of NH3 canceled, so it's mole H2O on top. And then I have 4 on bottom. 48 divided by 4 gives me 12 moles H2O. Now, according to this problem, I would need one significant figure, which would make me want to round this number down to 10 moles of H2O. Now, how do I know how many significant figures I have? I start with my given. My given is 8 moles, so that means I need one significant figure. But this problem is a little tricky because I'm given exact numbers in this ratio, but I'm going to go ahead and round it down to one significant figure and make it 10 moles of H2O. But I personally would probably still accept 12. Okay, next problem. This is going to be volume to mole. Volume to mole is a little special, and you guys already know that, because we get to use our 22.4 liters is equal to 1 mole when it's of the same gas. So if it's one gas in liters, you can say that 22.4 liters of that is going to equal 1 mole. But again, I'm getting ahead of myself. I got to balance first. So I have nitrogen, hydrogen, and oxygen. So 1 nitrogen, 3 hydrogen, 2 oxygen, 2 nitrogen, 2 hydrogen, 1 oxygen. I'm going to go ahead and start with 2. So 2, and now I have 6. Okay? That means I want to go ahead and do, well, I want an even number of these, so I'm going to go ahead and double this one real quick. And the reason why I know I need an even number of oxygens, or an even number of waters, is because it's H2O, and that's an O1, and I have an O2 on this side, and that means I can't end up with an odd number on this side because there's no way for me to get it, because I can't have fractions. So I went ahead and made that 4, so that gives me 4, and 4 times 3, 12. So I'm going to go ahead and put a 6 here again. That gives me 12. 6 times 1 is 6. I can put a 3 here. That gives me 6. And then nitrogen, I get to put a 2 again. And I just realized this is the exact same equation from the slide before, so I don't know why it took me that long to balance it. But that's okay. It's good practice. Okay. So I have the data that tells me that for every 22.4 liters, I'm equal to 1 mole. And I know that because it's my ideal gas law constant. And we're going to go ahead and assume everything's at STP right now because we haven't talked about gas laws yet. So I am given 12.2 liters of NH3. And I want to know moles of H2O. Okay, so I'm going to put my given number 1 again. Okay, liters of NH3 is going to go on bottom. If I have liters of one thing and I want moles of something else, I have to go through my mole. So I'm going to put moles of NH3 on top. And guess what? I have this special conversion piece of data right here. All right, I have moles of NH3 on top here, so it's going to come down here. It's going to slide on down. And then for every 4 moles of NH3, and I want moles of water. Oh, I guess I accidentally erased this earlier. That was 6. Moles of H2O, I get 6 moles. Okay? And I am going to have to use the calculator on this one. I'm not that good yet. So 12.2 times 6 is 73.2 on top. What are my units? Liters, liters, moles, moles, mole of H2O. Which I'm going to kind of write a little crazy off to the side, but that's okay. And on bottom, I had 22.4 times 4, which gives me 89.6. So then 73.2 divided by 89.6. All right, I was given 3 significant figures, so I'm going to end up with 0.817 moles of H2O. All right, so that was mole or volume to mole. So I had liters, so I had to do liters to moles, and I can use 22.4 liters for every 1 mole if it's the same gas. And then I did my mole to mole ratio using my balanced chemical equation. Let's do our next problem. Our next problem is going to be mass to mole. So in mass to mole, we have to use our molar mass, which isn't going to be a big deal because we are totally awesome at calculating molar mass. So let's go ahead and balance first. So I have calcium, I have carbon, and I have oxygen. This case, carbonate can't stay as one ion or one unit when I balance because it splits into CO2 and CaO. So 1 calcium, 1 carbon, 3 oxygen. 1 calcium, 1 carbon, 3 oxygen. Awesome. Already balanced. Don't even have to do anything with it. So if I don't have a number in front, I can assume ones, but I'm going to write them in just for no confusion going on here. So we're given 4.0 grams of CaCO3 or calcium carbonate. It's going to decompose, and we want moles of CO2 or carbon dioxide. All right, we're starting with grams of one thing and we're getting moles of something else. Well, to get from grams of calcium carbonate to moles of calcium carbonate, I'm going to need my molar mass. So that's going to be the piece of data that I'm going to go ahead and calculate. So to get this piece of data, I need to figure out what the molar mass of calcium is. When I look at my periodic table, I get 40.08, that's grams of calcium, and I only have one of those, plus carbon, which is 12.011 grams of carbon, and then I have 3 oxygens, and I know that molar mass is 15.999 grams of oxygen. So I'm going to add that number together, and that's going to give me my molar mass of CaCO3. All right, that gives me 100.088 grams of calcium carbonate, and that's grams per mole. What grams per mole means is that for every 100.088 grams of calcium carbonate, I have 1 mole of calcium carbonate. Okay? So I'm going to scroll down a little bit because I took up more room than I was expecting to take up, but that happens all the time. Okay, this is all the information I really need. So again, I'm going to start with my given. I'm going to switch to blue. So I start with 4.0 grams of CaCO3. I put the number 1 because it's my given. All right, I have grams of calcium carbonate and I want moles of CO2. So I need to get this grams to moles. And I can do it with my molar mass. Good thing I just calculated it. So grams of CaCO3 goes on bottom and moles of CaCO3 goes on top. I know it's grams that way because grams is up here, so now it's going to be down here. So my molar mass is for every 1 mole of calcium carbonate, I have 100.088 grams. Okay? So that's my molar mass conversion. So now I have moles of CaCO3 and I want moles of CO2. Good thing I have this balanced chemical equation and I can do that mole to mole ratio. So moles of CaCO3 goes on bottom and moles of CO2 goes on top. Okay, so that's a 1-to-1 ratio. I'm going to go ahead and cancel my units out first this time. So grams CaCO3 are on top and bottom. Moles of CaCO3 are on top and bottom. And I end up with moles of CO2, which is exactly what I wanted. And I'm just going to work this out in my calculator all together. So I'm going to do 4 times 1 divided by 1 times 100.088 times 1. And I'm going to do that all in parentheses. Or I can just do 4 divided by 100.088. All right, I started out with 2 significant figures, so I need to end with 2 significant figures. So it's going to be 0.040 moles of carbon dioxide is my answer on this one. Remember, these first 2 zeros don't count because there's not a significant number in front of them. Okay, next problem. This one is a mass to mass. In mass to mass, I have to have the molar masses of both the compound of my wanted and of my given. And that's okay, because we're going to calculate that first to save us some time. Again, same equation as last time, so I know I can just do 1, 1, 1. Perfect. All right, we're given 45.0 grams of calcium carbonate. And we want grams of CO2. So my data in this case is going to need to be some molar masses. So I'm going to know for every 1 mole of CaCO3, I got to calculate that molar mass. Well, I did that the slide before, and I already showed my work, so I'm just going to skip back real quick and see that it's 100.088 grams. And you can rewatch that part of the video again if you need help on that. Now CO2, so for every 1 mole of CO2, I need to know how many grams that is. So the molar mass of carbon is 12.011 grams, and oxygen, which I have 2 of them, times 15.999 grams. And this number here is 44.009 grams. Okay, I'm guessing my grams of CO2 per 1 mole of CO2, because that's my molar mass. And I'm just going to erase this because I want to save some space. Okay, so I'm going to do my gram to gram conversion now. Here we go. Switching to blue again so you guys can see what I'm doing. So I start with 45.0 grams of CaCO3 over 1. All right, I have grams of CaCO3 on top, so it's going to move over here to the bottom. And I have grams of CaCO3 and I want grams of CO2, so I have to go through the mole, and I happen to have a conversion factor that'll let me do that. Right up here, for every 1 mole of CaCO3, I have 100.008 grams of CaCO3. All right, moles of CaCO3 is going to go on bottom. All right, I have moles of CaCO3 and I want grams of CO2, so I have to do a mole-to-mole conversion. And again, it's a 1-to-1 ratio, which is going to save me some math. All right, moles of CO2 was on top. Now it goes on bottom. I want grams of CO2, and I have the conversion factor of my molar mass already calculated. So 1 for every 44.009 grams. Okay? Again, I'm going to cancel my units to make sure everything works out. I'm going to multiply everything on top together. So 45 times 1 times 1 times 44.009. And I'm going to divide that one in parentheses 1 times 100.008 times 1 times 1. Or just 100.008, because you know those ones aren't going to affect it. Okay? All right, I started out with 3 significant figures with 45.0, so I'm going to end with 3, and that gives me 19.8 grams of CO2. And that was a gram to gram conversion. Okay, there's our gram to gram conversion. All right, let's do our next one. All right, let's do a mass to volume. So mass to volume is we're going to start with mass of one product, and we're going to end up with volume of the other one. Or it can be 2 reactants. In this case, it just happens to be 2 products. So let's go ahead and balance to begin with. So aluminum's the same on both sides, and chlorine is a little bit different. So I have a 1-to-1 on aluminum, but I have a 3 3 to 2, which means I can easily make 6 if I make that a 2, and this a 3. And that also makes this a 2, so we put a 2 right there. Okay, let's go ahead and figure out what our given is. Because I told you it's mass to volume, I know my given's going to be a mass, and I was right. It's 0.98 grams of aluminum. And I want liters of chlorine gas. Okay? Remember, chlorine is one of our diatomics, so it's Cl2. And we can remember the list of our diatomics from the lovely phrase of Brinkelhoff. So, I need some data in order to solve this problem. I have grams of aluminum, and I need to figure out how to convert that to moles, and I can do that with my molar mass. I'm pretty lucky this time because the molar mass of aluminum is just what the periodic table tells me. So that's going to be 26.982 grams of aluminum is equal to 1 mole of aluminum. All right, I have liters of chlorine, and I'm going to want to get that to moles. Good thing I know that I can use 22.4 liters is equal to 1 mole. Because we're going to assume all of our problems are at STP if we're going to have a gas involved right now. Okay, have all my data. I have my given and my wanted. I can go ahead and set this up. Again, I put my given over 1. 0.98 grams of aluminum over 1. Okay, grams of aluminum was on top, so it's going to go ahead and go to bottom. If I have grams of something and I want grams of something else, I obviously have to go through my mole. The answers always go through the mole. So, moles of aluminum is going to go up here in my numerator because I have grams in my denominator and I have this lovely piece of data right here. So for every 26.982 grams of aluminum, I have 1 mole of aluminum. Mole of aluminum is in the numerator, so it's going to hop down here to the denominator. All right, I have moles of one thing. I want I want liters of something else. Sorry, if I said grams earlier, I want liters of something else. So I'm going to do my mole to mole ratio. So for every 3 moles of chlorine, I need 2 moles of aluminum. Last step. I have moles of chlorine now on bottom, and I'm going to get, not grams, but liters of chlorine. Okay, 22.4 liters is equal to 1 mole of the same gas at STP, and we went ahead and assumed it was at STP. Grams, grams, moles, 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 and I end up with liters of Cl2, which was in fact my wanted. Okay, everything on top multiplied together, 0.98 times 3 times 22.4. I'm going to divide that by 26.982 times 2, and I put that in parentheses so I don't get a weird answer. Okay. I started out with 2 significant figures, so I'm going to end with 2 significant figures, and I get 1.2 liters of CO2. Okay, that's a mass to volume. Our next one is a volume to mass, so it's the opposite. We're going to reverse the steps. So the good news is we've already calculated all the data from the page before, but we didn't really have to calculate that much to begin with. So that's going to save us a little bit of time. I'm going to skip back real quick to make sure I get my balancing right. 2, 2, 3. Okay. I'm given liters this time, and I'm given 5.09 liters of chlorine gas, Cl2. And I want, or my wanted, is grams of aluminum. All right, data time. If I have liters, I'm going to need to go through moles at some point. So I'm going to go ahead and put down that 22.4 liters of one gas is equal to 1 mole of the same gas at STP. And we're going ahead and assume an STP right now. All right, I need that molar mass conversion. So grams of aluminum equal to 1 mole of aluminum. I get that straight from my periodic table. Again, that number is 26.982. Okay. Switch into blue so you can see everything. So put my given over 1. All right, liters of chlorine. chlorine was in the numerator, it's going to slide down to the denominator from top to bottom. Right, liters of chlorine, I need to convert through the mole, so I'm going to go ahead and put moles of chlorine on top. Okay, for every 22.4 liters, I have 1 mole. Okay, moles of chlorine on top, we're going to go ahead and slide that down to the denominator. Okay, moles of chlorine's down here. I want grams of aluminum, so I'm going to go through moles of aluminum to get there. All right, for every 3, I need 2. Okay, moles of aluminum was in our numerator. We're now going to put it in bottom in our denominator. Moles of aluminum, and we wanted grams of aluminum according to our wanted. Good thing we have this molar mass here. Okay, again, everything on top together divided by everything on bottom. All right, I started out with 3 significant figures. I'm going to end with 3 significant figures. 4.09 grams of aluminum. All right, that is volume to mass. It's just the reverse steps. So before we used our 22.4, down here where we used our molar mass. So we just kind of switched them. We made them fit with the grams goes with the molar mass and liters goes with volume. All right, last thing, limiting reactant. So a limiting reactant is a little bit different, but kind of the same. The thing is, you're going to have 2 separate givens, and you're going to solve for the wanted, but you're going to solve for it twice. And we're looking for the one that produces the least amount of product, because that's going to be the reactant that limits our reaction. Okay? So first thing we're going to do is balance. All right, Mg and O are my only 2 elements. 1 Mg, 2 O, 1 Mg, 1 Mg. So I'm going to put 2 here, and I'm going to put 2 here. And I'm going to go ahead and put a 1 there, just to save us any possible confusion. Okay. So I'm going to have 2 different givens. My first given is going to be 7.24 grams of solid magnesium, or Mg, and 14.86 liters of oxygen gas. Remember, oxygen is a part of our diatomic group, so that's why it's O2. They're going to react to form magnesium oxide. We want to know how many grams of magnesium oxide are going to be formed. And we want to know which one's going to limit that reaction, which is kind of what the whole limiting reactant thing is looking for. So I have my given on this side and my wanted, and I'm going to go ahead and put the data that's going to coincide with each one on this side. So for grams to get to moles, I have to have my molar mass. With magnesium, I get to use just that number that's already printed on the periodic table for us. It's a little less math there. So for magnesium, I have 24.305 grams of magnesium is equal to 1 mole of magnesium. All right, liters, and I want to get that to moles, so I get to use 22.4 liters is equal to 1 mole of the same gas. In this case, we're using O2 as our gas. All right, last one. We need magnesium oxide. We need the molar mass of that. So for that, I take the mass of magnesium and the mass of oxygen, and they're in a 1-to-1 ratio. So 24.305 grams plus 15.999 grams. And I'm going to write that number right here. That gives me 40.304 grams of magnesium oxide is equal to 1 mole of magnesium oxide. And then again, I'm just going to erase this so I can save me a little bit of space, because I'm going to take up quite a bit of space on this one. And I'll probably be scrolling up and down a lot. Hope I don't make your car sick. Okay, here we go. Let's do our first given right here. I'm going to do one of my givens in blue, and I'll do the other one in green so you can compare them to each other. All right, first one, 7.24 grams of magnesium over 1. All right, start with grams of magnesium here. Put grams of magnesium down here. I have grams of magnesium. I want grams of magnesium oxide. I have to go through the mole, and to do that, I have to get to the molar, I have to use my molar mass to get to moles of magnesium. My molar mass tells me for every 1 mole of magnesium, I have 24.305 grams of magnesium. Okay, moles of magnesium, I'm going to move down here now. And I can now compare moles of magnesium to moles of magnesium oxide. And I get to use my balanced chemical equation to do that. So for every 2 magnesium, I get 2 magnesium oxide. Last step. Moles of magnesium oxide are going to move down here now. And I wanted grams of magnesium oxide. I get to use my molar mass for this. Okay? So, what I'm going to refer to as my blue reactant or my magnesium reactant is going to be so I'm going to do 12.0 grams of magnesium oxide. Okay? So that's my first one. And I'm going to go ahead and box that in so it's easy to find later. All right, my next one I'm going to do in green. In this case, I start with liters of oxygen. So 14.86 liters of O2 over 1. Okay, before I use molar mass to convert to moles, but since I'm in a volume, I'm going to use 22.4 liters of O2 to convert to 1 mole of O2. Because again, we are still assuming STP, which is standard temperature and pressure. All right, moles of oxygen in my numerator, it's going to slide down to my denominator. Okay, moles of O2, and I'm comparing that to moles of MgO, because I want grams of MgO, and I have to go through my mole. So for every 1 mole of O2, I have 2 moles of MgO. Last step. Again, I get to repeat this part right here. I just slap this down here. So I had 1 mole of MgO, and then I get to put my molar mass of MgO on top, or magnesium oxide, because I'm still solving for grams of magnesium oxide. So do that math one more time, and then refer to this as my green reactant, which is still oxygen. Okay, that's a much bigger one. 54.5 grams of MgO. All right, to determine my limiting reactant, I need the one that produced the least amount of product. Who produced the least amount of product? It's gonna be magnesium, because I only got 12 grams there, where down here I got 53.5. 53.5 is a lot bigger than 12. So I'm gonna go ahead and write magnesium is limiting, which means oxygen is in excess. Okay, so we've gone ahead and hit on our solubility rules today. We predicted some products. We did a net-ionic equation, including our particulate diagram. We did a little bit of everything in stoichiometry, and we ended up with a limiting reactant. I also threw in some balancing along the way, and I talked about significant figures a little bit. So hopefully this helps you guys out with all your questions. If not, email me or come see me in class. Good luck.